Okay, I think we'll get started. Good afternoon, everyone. Thank you for your time today. I would like to begin by acknowledging the traditional custodians of the land on which we meet and pay my respect to their elders, past, present, and emerging. My name is Mortaza, and I am the training coordinator for the Australian Space Data Analysis Facility, also known as ASDAF. We've got a live audience as well as we're streaming the event as well. So we've got some people joining us through WebEx as well. So I'll just talk a little bit about ASDAF before we move on to the presentation. So ASDAF is an Australian space agency initiative with the aim of helping Australian SMEs and researchers leverage space data, and we do this through 4 core services. So we provide access to high resolution data, space data, satellite data. We provide access to tools and expertise to analyze those data. We provide training and consulting services to SMEs and researchers, and we work with research organizations and data programs across Australia to promote the space data sector across Australia. So if you're interested in trainings and seminars, we conduct trainings and seminars very frequently. So just keep an eye out on our website for that. So ASDAF is supported by a few organizations. Our work is supported by the federal government, the Australian Space Agency, and the West Australian government. Our work is delivered in partnership with the Curtin Institute of Computations, the Pawsey Supercomputing Centre, and the WA Data Science Innovation Hub. We've got a very exciting presentation today. Our speaker is Dr. Tristan Campbell. So Tristan is an experienced geoscientist with over 20 years of experience in applications of remote sensing and geophysical methods to engineering, environmental, and agricultural sectors. His doctoral research resulted in a method for quantitative prediction of honey harvests in Western Australia, which is available to the bee industry through a geospatial portal for beekeepers to assess site weather conditions and expected harvests. Tristan is currently researching methods for improving weather data accuracy as model inputs and the effects of fire regimes on honey production and biodiversity. Tristan, over to you.
Thank you very much. Should lock them enough for me, so
Just the arrow.
is the microphone on mute?
Oh, it's just this microphone. Yeah.
Okay, cool. Thanks.
Yeah.
Well, thanks everyone. Welcome everyone here in person and online. My name is Tristan Campbell. I had a bit of a circuitous route into this particular research area. So I graduated from Curtin University last millennia, 1999, doing geophys undergrad here. And I spent about 15 years out in the industry doing environmental agricultural engineering work around groundwater and soils and all kinds of random things. About 10 years ago, I jokingly said to my wife, we should get a beehive for our backyard just for our
That's okay, because we're using the microphone as a laptop.
Yeah. Thanks. All good. So yeah, and as a joke, I said one day we should get a beehive for our veggie garden to help pollinate the veggies, get more veggies out of it. And she took that as a suggestion rather than a joke. Told me next month I was going to buy her a beehive for her birthday. We got a beehive. We got a few more beehives, and then we wound up running a business. So my wife and my kids and I run about 50 beehives around WA. We're considered quite small, so to be a commercial beekeeper, you need at least about 300 or 400 beehives to make a living off it. So 50, while it's a lot of bees, is not a lot as a full-time job. Then I started my doctorate when I was looking at trying to work out ways to improve how we can manage our beehives and predict where to put bees, different locations around the states for honey production. So that started my doctorate a little while ago, and now I'm sort of in this space, and there's also further applications from this research. If you look at nectar and honey production as a measure of ecosystem health and ecosystem services. So I follow on applications for this idea in terms of if things aren't flowering, then obviously the reproductive cycle is maybe having issues as well. So that's a bit of background about me. But why bees? certainly in the last 10 years, since we had a beehive, conversation has changed from our bees sting people to bees are important to us. So it's been great seeing the general groundswell of support for pollinators. The general stat you hear about bees is they pollinate 1/3 of all food that we eat, which is kind of true, but also that's actually across all pollinators, and it's 1/3 of the variety of foods, not the volume of food. So if you look at the amount of grain we consume, it's not 1/3 of our food, but certainly the variety and most of our colourful foods and everything are bee pollinated. Most people think of honeybees when they think of bees, but that's just one species. So all the honey produced in Australia, and indeed most of the world, is from the European honeybee, but that is only one species out of many, many bees. So globally, there's 25,000 species of bees, 2,500 in Australia. It says there are 30,000 species of wasps, ants also are a similar family, ants do pollination as well. So look at some of the varieties. You've got you see these in Perth or WA quite often. These are the blue banded bees. These are a native bee, an iridescent bee from South America. This is the Dawson's burrowing bee from the Midwest in the Gascoyne. And this is one of the world's largest bees. It makes burrows, and the bees are about, I think, 3 centimeters long. But interestingly, in Australia, all of our native bees are stingless. So we have, the most venomous, snakes and jellyfish and spiders stuff. Most people think about bees as stinging people, but all of our native bees are stingless. They all bite you, but most of them are pretty harmless. We go on to wasps, and even wasps do a lot of pollination, and most wasps are pretty harmless too. So you think of wasps, you think of the European wasps, and they're pretty vicious. Again, like bees, most wasps are not like that. So this is actually a photo of a wasp we had near our front door. It actually lays a circular mud nest every year. And we walk by every day, and it's absolutely fine. So there's wasps. While yes, the European wasps are rather nasty. Most wasps are pretty docile, and they're pretty chill. They can look pretty vicious, but again, don't believe all the hype about them. One of the things in WA is we've got a very diverse range of flora, such so we have even mammals and marsupials that live on nectar alone. So this is a honey possum, lives down the south coast. It weighs about 10 grams, and every day it consumes 7 grams of nectar and 2 grams of pollen every single day. And that means that a whole year round, there must be enough nectar to sustain populations of these guys. So the diversity of flowers and availability is quite amazing. This is another picture just for scale. So they're absolutely tiny little guys. And they have the largest testicle to body size ratio of any animal, just so you know. It's a little fact. So you can tell what's important to the guys there. So if we just focus on the European honeybees and sort of how the hive works, when you think of bees and hives, often you think of the queen bee. And everyone thinks, well, the queen bee, she's the queen, she's in charge. It's actually much more like Australia, where it's a constitutional monarchy, where she does work as tell her to do. So she lays all the eggs. She's the only fertile female. Peak season, she might lay 2,000 eggs a day, but she does what the workers tell her to do. The workers do all the work. So while they go through different phases in their lives in terms of being a nurse bee or a guard bee or an engineer bee or a foraging bee, they are the same bee as different ages, and they're all female, and they're all infertile. So all the work is literally done by the girls. The boys are called drones, and they're pretty useless. As my wife says, when she goes to school groups, all the boys do is wait for a girlfriend, and that's it. They can't even feed themselves or clean themselves. So the girls do literally everything. We're very lucky in WA in that for bees, we've got we're not facing all the issues that are overseas. One of the biggest things is the varroa destructor mite. You can see there on the right, and it's basically a tick for bees. But you think of like a kangaroo tick or a pepper tick, and that can paralyze a human. The varroa mite, if it wasn't a human, is the equivalent size of your fist, and it latches on the back of a bee's neck. And basically, it doesn't always kill them, it really weakens them, and they transmit diseases and things as well. So the varroa mite is behind a lot of the initial issues with declines in bee health around the world. Then there are issues around pesticides and everything as well. But that's one of the main things. Our biosecurity here is really good, and we're actually luckier again in WA in that there are some pathogens on the east coast we haven't got here. So when you catch to throw your honey out at the airport, please do so. It's really, really important. We also have a high biodiversity here. We mentioned that in terms of the nectar available year around in some areas. Good climate, so generally it's not too hot, generally not too cold, so the bees can fly most year round. They haven't got to be rugged up inside the hive for snow and things normally. And as this video shows, when there's a good season, we produce ridiculous amounts of nectar from our flowers. This is a mallee flower from Laverton in the desert. And it produces a lot of nectar. Even we had bees out there about 1,000 k's from Perth a couple of years ago, and it's obviously mostly red dirt effects, but even the sparse number of trees there was able to produce a good amount of honey from effectively a desert environment. So we've got some really good things going for us here. In WA, honey is produced in sort of the southwest corner, so out to the goldfields a bit, but mostly in the forests up and down around the coast area. So when we started having a beehive, there was about 500 beekeepers in WA. There's now about 4,000, but almost all of those are hobbyists who have 1 or 2 hives in the backyard. Number of commercial beekeepers has been fairly stable. There's about 30,000 commercial hives, and the map here is the commercial leases apiarists can have from the government on Crown land. And so we're very lucky in that a lot of our production comes from native natural forest and Crown land, thin environment, limited access to chemicals, pesticides. It's pretty good. So our production period is production spring through to autumn. So typically you think of the wildflowers through the Midwest, and there's lots of wildflowers and they're very pretty. Not a lot of nectar, but that's when the bees they realize it's springtime, they get busier, and then once the gum trees start flowering, that's when you generally get the main production. So most beekeepers, if you're looking at commercial scale, they move their bees from as far north as Kalbarri area, so they'll winter up 400 k's north, and as the spring flower front moves south, they'll actually track the beehives further south, and then often wind up as far south as maybe Bunbury or Nannup region for summertime, and then moving back further north again for winter. So it's very much a migratory practice. But you do occasionally there's some good unusual winter honey coming in at the moment right now from Yate Gum on the south coast, and that's a 700 k drive from Perth to the bee site. So there's a lot of driving involved with making sure to optimise production. And we actually hold the record in WA for the most honey produced in a year by a single hive, which is 350 kilos of honey from one hive in 1 year back in the 60s. Average production in WA for a commercial keeper is about 200 kilos per hive. East Coast is about 100 kilos per hive. In the UK, it's about 10 kilos per hive. So we are very, very lucky. As I said, good climate, almost no pests, good country for production. So we're very, very lucky here. On the flip side, because we rely on forests for our production, it's a more complex flowering cycle than for agricultural crops. A lot of gum trees don't flower every year, and even some species in the same forest might have different triggers for flowering. So to go to the east coast for a minute, this is results from a study done from ironbark forest, the main production forest over east, from 4 different species. And of these 4 main honey producing species, each one had a different trigger for peak production. So the red ironbark was affected by both the minimum and maximum temperature range in terms of honey production. Yellow gum was only affected by minimum temperature. The grey box only affected by maximum temperature. And then the red box was by the average temperature. Basically, you can see how each of these species have developed their own climatic triggers for their flowering cycles, so that you're not locked to have all 4 species in full flowering mode at the same time. So they'll pick different years for their flowering to maximise their cross-pollination. In WA, Marri or red gum is the main is one of our mainstay harvests. It's a good harvest every couple of years normally. This is a video from some of our hives near Roleystone, and you can see the white on the trees there. And when they flower well in a good year, this is about 3 years ago, you can produce a lot of honey pretty fast. So this is a sort of a late summer flowering tree. Jarrah is one of our more sort of famous ones. It's more well known for its medicinal properties, and it flowers about every 3 to 4 years-ish. Again, it does vary a bit, but it does have quite a long period in terms of it takes 12 months to go from a bud into an open flower. And if you get too much stress for any reason in that 12 months, it drops the buds and it starts again. So it's quite it's a very high value honey. It's quite a fickle thing to produce as well. And then the carrier, which holds the record for the most honey produced in a single hive, only flowers every decade or so. These are the world's 3rd tallest flowering plant. They're 80 meters tall. You can see from the drone footage, it just keeps going up. And when they do flower, they flower for about 6 months, and the honey just comes in for a long time, but not very often. What we're seeing in the last probably 2 decades is a change of pattern where you'll have, rather than having the whole carry forest going off every 10 years, you'll have small patches here or there every year or 2. And so it's looking like at this history of these massive big honey flows where you could continually harvest honey for half a year. It may almost be finished up now. So Maori honey, it's sort of currently Jarrah's poorer cousin. Interestingly, it actually has higher medicinal properties on average than Manuka and Jarrah. So as a scientist, I do get annoyed with the whole let's buy Manuka, it's going to cure cancer and things, because the property that it's been sold for is antimicrobial property, it is very good. All the science behind it is topical use on wounds, not eating it. It is good to eat because it's honey, and honey's got all kinds of other stuff. But the actual number you're paying for on your jar of Manuka or red gum or Jarrah is actually around topical application for burns and ulcers. And for that application, it is superb. It really is. However, Jarrah and Maori often have higher levels of antioxidants and prebiotics than Manuka. There's been some small preclinical trial studies actually showing honey can be used to treat diabetes, which is a bit odd given that it's sugar. And the first trial went out to show that honey is just sugar, and they had a small sample of about 20 diabetics, had 10 on 2 tablespoons of honey a day, so that's a lot of honey, and then 10 control. And after a couple of weeks, all of the diabetics on the honey diet had massively reduced or stopped the insulin. And that result has been replicated many times since that point. That the issue is honey is a very complex compound, so it's about 700 different chemical compounds in the honey, and they can't actually figure out how to make it in a lab, and also what combination of those compounds interacts to get these results. It's really quite an interesting area. Maori flowers most years, so for beekeepers it's quite good. It's not every year, it does flower some years, and it does vary, but you can generally get some Maori for some location every year, so as a reliable crop it's decent. And the nectar and pollen is very good for the bees. So not all nectar and not all pollen is the same. So with bees, they prefer a high glucose nectar. If the fructose is too high, they'll ignore it and they'll actually fly past flowers that are dripping with nectar if the ratio isn't quite right. So in terms of both the product value and the bee health, it's very important for our industry. As mentioned, it's sort of a summer to early autumn flowering period. Interestingly, the Maori and Jarrah that start flowering in this Great Southern region, and then move north of Perth, whereas pretty much every single other flower in the state starts flowering in the north and moves south. And there's no idea as to why that trigger occurs, but it's documented very clearly. So you find the Maori trees north of Perth, so north of Gingin, they start flowering generally about a month after the ones sort of down south around Bridgeton area. Again, there are patches that vary, but that's the general rule of thumb. And interestingly, having flowers does not always mean having nectar or honey. So Jarrah and Maori both often produce pollen for the first couple of weeks, which is very important for the bees. The pollen is the protein source for the larvae. Without pollen, you can't grow healthy bees. And on the picture, you can see a bee with what we call pollen baskets on its back legs. So what the orange dot on its back leg is actually where it's had a bunch of pollen dust in it. It's cleaned itself off. It's made it into a ball, put a bit of bee spit in there, and it's stuck on its leg. And that's how they collect pollen back to the hive. So you find as the larvae are fed bee bread, which is pollen dash honey, and the adults have a higher nectar diet or honey diet because they've already grown. They more need the energy to work, not to grow. So having that pollen store is very useful. And in terms of the timing of the flowering period for the Mary, it's generally the last honey flow before winter sets in. And so you need to, if it's important to have a good flow at that period, so bees can build up stores and health for the winter period when there's a few months there's not a lot of food around. As mentioned, it varies a lot. So this is the research that the sites had research data from to date for the project. And you can see, so I've got box whisker plots here where you've got your maximum and minimum every year, and then your 25% value, your mean, so median, and 70%. And you can see year to year it does vary a lot. So this is across all the sites. And you can see that one of the interesting things is that after a good year, there's never another good year. So you can get, when you have absolute bumper crops, there's almost physically no space for flowers next year on the trees because there's still nuts there instead. They just can't actually find space to put flowers out. So general rule of thumb is after a good year, you'll have a lower year. But you don't always after a low year get a good year because you still need to have the right triggers to go from, you can see here was quite a low year, following year, the weather wasn't quite right, and then the year after that it was a 3-year gap from good year to good year. So while yes, there's some flowering in most places, most years, the variability in terms of going from 70 kilos per hive to 0 kilograms per hive across the years is a difficult thing to manage. And this is looking at individual sites now. So across the 10 years of data, you can see sites on the very left in the Perth Hills where it's full forest, going from 70 kilograms to 0 kilograms depending on the season. So these orange ones is from this kind of environment here. And then farmland is these orange ones is this kind of site here where there's not that much forage around. Some of these only have maybe 5% of actual canopy cover, but you can still produce 20-30 kilograms of honey per hive, even from quite sparse trees in those areas. And then the blue sites on the left are this sort of mixed use where you'll have some forest and some rural areas as well. But you can see for each of these individual sites, the range is quite significant. One of the great things in the last few years has been the advent of drones. As you saw from the video earlier, decent sized trees, big white flowers. It's very easy for a beekeeper to go to a site, pop a drone up and see what's going on. It is important because particularly when you're trying to look at the forage ranges for bee, which is a K or two from the hive, it's very hard to get a feel from the ground as to what's in that sort of radius of forage area. Also, when you'll generally get trees flowering better on roads or roadsides with a higher solar exposure and higher sunlight, means you can't use what you see on the side of the road as indication of what's going on in the bush. So the drones are very useful for that. And so we're working on some algorithms to basically take drone data and quickly give an indication of percentage canopy and flowering over time. So this is red gum forest at the very, very start of the flowering period. And from the ground, you can see nothing flowering, whereas you got, of course, the color quality is not great, but there's a flowering tree there. So there's actually a lot flowering in this space, but from the roadside, you can't see very much. So the ability to just even have a quick visual inspection for a beekeeper is pretty handy. We start going towards more the satellite side of things. There's the amount of freely available satellite data has changed a lot in the last few years, which is one of the reasons why ASDAF is a great resource to have. One of the things to look at is what actual system you choose in terms of your sensor and your data. And one of the ways to do that is doing spectral analysis of your targets. And so this here is a result of doing field surveys and going out with a handheld spectrodiometer, measuring the response in different wavelengths from your visible light, visible wavelengths through here, and then through your through near infrared, short infrared, far infrared. Basically, you can see through here that the flowers are in blue, and they're very bright in the visible spectrum. There's actually they sit in between the ground and the flower response, so the leaf response through the infrared, and then far infrared they actually sit quite low through there. So this means you can start looking at, okay, where's the greatest difference between your target, in this case your flowers, to everything else, and in this case the biggest separation of the spectral response is very much from the visible range. While it's obvious when you look at flowers, they look different to the plants. Often there may be in other target things, like in terms of your leaf types or geological use, there's actually non-visible spectra that are much better for separation of features. Not so in the case with the flowers. And then, so we know we'll want to look at these bandwidths or these wavelengths for analysis, and then you start looking at, okay, what do you want to do with it? You're looking at an annual information, or you're looking at detailed spatial variability. Is there a very tight bandwidth you need to find for it? And this is when you start looking at what kind of sensors you want to have. And so the three main things you're looking at is spatial, so pixel size; spectral, how tight the bands are, how well it resolves to parts of the spectra; and then temporal, or revisit time. And generally you can get one or two of these three things. You can't get all three at once. And it's a function of, basically, if you think of taking a picture during the daytime versus nighttime, there's just less light coming in. And so if you have a higher spatial resolution, there's less actual photons hitting the sensor than if you've got a broad pixel. And so you'll find if you have a very high spatial resolution, you find that you need to have literally a satellite lower down, which has to move faster. So things like the Himawari is a geostationary satellite. So it sits above the equator. It actually was launched by the Japanese Space Agency. Luckily, we're south of Japan, so it covers us. And this has got an incredible return time, because it is literally, it sits there and just takes a picture every 10 minutes. Lots of data, really fast. But in terms of spatial resolution, you can't pick up a lot of detail compared to other systems. So you need to consider what your use is compared to the specifications. So if we start looking at how I want to predict this stuff, ideally, as you could see, there was the annual variability is very high. So if the beekeepers know ahead of time it's going to be a good, bad, or poor season, they can plan around, do we need to increase our number of beehives to maximize production in a good season? Or do we need to actually start reducing our numbers and plan to put more honey aside or pollen aside for stores for winter time? If you get that wrong, you can damage it pretty badly. And then once you get closer to the actual start of production, which sites we're going to use, which looking promising, and if you got bee sites from Bridgetown to Gingin, if you can reduce time actually driving around looking at trees, that's pretty handy. The big goal long term is to hopefully develop something like CSIRO's Graincast for honey. What CSIRO has done over a long period, they've got very sophisticated crop growth models, and every couple of weeks over the season, this is taken today, they do a prediction of the yield probability this is for WA, and actually go down to paddock-specific yields of different crop types. And as it gets closer and closer to harvest time, the error bars get smaller and smaller. Obviously, there's a few months until actually even really start to grow the crops. So a lot of unknowns. It gets closer and closer. And then there's the companion app, which is being merged into a new platform now, where a farmer can walk around the paddock and they go, I'm here, I want to plant barley. And it'll actually pull out from the national database what the expected yield is and the uncertainty of that yield for that season. That's the end goal, but we're a little ways away from it at this stage. So this was decades of work and a lot of funding. So far, it's been PhD, so not quite there yet. Most of what I am going to talk about now is actually in the article there. You can see machine learning regression, and so you can look at more details there if you like. Biggest thing around models is GIGO, garbage in, garbage out. And so this goes back to obviously your looking at your site locations, your satellite data, your weather data, and it's very easy, especially with the amount of computing power and amount of data you can get, to assume I've got lots of data, I've got a fancy computer, I'll throw it all in, and it's going to be a great result. And it's actually probably more likely to give a really bad result because you haven't gone through the process of really culling it and making sure you know what's going on through the whole process. Inputs were used. So obviously we want to look at honey harvests. So a lot of you saw the map of the sites. Most of those sites you got multi harvests, and we basically normalized it to number of kilos per hive as sort of a standard number we could use. We are lucky in WA, and all beekeepers pretty much get their queen bees from the same location on Rottnest Island, which has got the world's longest running and best quality queen breeding program in the world. And so all of our genetics, while there's variations, there's consistency there as well, which is one of the variabilities, is the queen bee quality affects the hive temperament and productivity a lot. So having that as a standardized part of our industry is actually pretty handy. We basically went through and while we worked on the actual kilogram numbers, we also used, we classified as a poor, moderate or good year based on the harvest, and the cutoffs were at 20 kilos and 40 kilos to go from the breakpoints. And that's based on the average hive setup. So you can see here a hive, and so you have your hive entrance into the brood box. That's where the queen lives, and that's where the nursery is and the larvae and everything else. And the honey boxes go above that. And basically, it varies a bit depending on the exact size of the box and everything as well, but rule of thumb, one box of honey is 20 kilos. So in terms of giving information to beekeepers that's sort of operationally meaningful for them, if you use those 20 kilo breakpoints, then if we say it's going to be a poor year, one box, moderate year, 2 boxes, good year, more than 2 boxes. So it's a very handy rule of thumb to use for the industry. There's a lot of inputs we can choose for this stuff. So weather is obviously an important one. And in WA, we've got on-ground weather stations from BOM and DPERD. We've got gridded products from BOM. We've got satellite products we can get. We've got satellite products calibrated by ground as well. And depending on where you are, the accuracy of these various products varies a lot. So in terms of the Maori, we're looking at the southwest corner, and it does have a fairly high density of weather stations. So we have found that the weather stations are the most reliable area. But if you're looking further out in the desert regions or pastoral regions, you will need to look at more likely a satellite derived or satellite calibrated response to get the best data through there. So this is looking at the average error for max temperature, minimum temperature, and rainfall for weather stations, gridded weather stations, raw satellite data, and calibrated satellite data across there. And so you can see there are some variabilities. And if you look at this compared to January, you can see there's definitely strong differences between the annual patterns to the January patterns, and then January to July in terms of winter to summer. There's big differences there as well. And so looking at the both spatial and seasonal accuracy of your products is important. And with the increasing occurrences of summer rainfall with the changing climate through the southwest, that makes things more difficult again, because you can have those intense summer storm cells and maybe 2 or 3 k's across, and you can dump a lot of rain in half an hour in one spot. And that's going to give a very different response to 5 k's down the road where it was dry. So the weather input is one of the key factors for this model. There's been a number of studies around the world looking at vegetation indices, so greenhouse indexes, moisture indexes, gross plant productivity, all kinds of acronyms I could throw at you for that. and a lot of them used for different types of models for nectar and honey production in the world. So we in terms of the data quality, in terms of spatial resolution, temporal resolution, and spectral data, we chose the MODIS data sets for this particular case, partially because bees have a forage range of about 1 to 2 Ks. So the 1 kilometer MODIS pixels are a good proxy for an average forage area. We are trying to do fortnightly or monthly iterations of the product as it comes closer in. And so things like Landsat, while they've got a lot more detail, you can't rely on them every 16-day cycle to get a good picture for you. If you have a cloud cover on that particular day when it does the flyover, then you've lost that part of the data set. Just some information. So this is where you can source national and gridded products for BOM. They do this. They produce on a daily basis. And you can do deviations from mean. You can do daily, monthly, annual maps, rainfall, temperature, soil exposure, humidity. So there's a lot of data you can download from there. This is the JAX one, the 10-minute data. So this is an example of their rainfall product, and you can download their rainfall product from here as well. And then for vegetation stuff, the Sentinel Hub from the European Space Agency. This is a great way to go through and not to download the data for analysis, but you can quickly go through and look at your various indices and different data qualities very quickly. And this is, compared to 10 years ago, this is now all free as opposed to behind a paywall or anything else. So going through, we've chosen data sets and we wound up with a 200-dimensional matrix. So we had looking obviously the honey harvest and location, a bit of information around when there was last wildfires through there, looking at monthly values for temperature, rainfall, transpiration, NDVI, and then looking at at seasonal ones, so November versus summer as well. So there's a lot of different permutation combinations as to how you want to look at the data. Of course, it is handy just to go through and just do some basic scatter plots, and based on talking to beekeepers and our own personal observations that we've had over running bees ourselves, where do we think we're likely to get some key information? And this is just looking at January and February values for temperature and rainfall. And across the x-axis, you've got kilos per hive, and graded into the poor, moderate, and good quality. And you can see that there's January maximum temperature has some very strong clustering around good quality harvests. If you get too wet in February, it rains too much, it washes nectar out, you don't get a good harvest. And so already you can see just from some very basic eyeballing, you can see some good patterns there. You start looking at combination and scatter plots of multiple variables, then you can see the clustering in certain areas, it becomes a bit tighter again. Of course, it's difficult to go past 2 or 3D plots of data to the human eye. Hence, when you got the 200 plus variables, that's when you want to start looking at machine learning areas. But even just doing some cutoffs on these parameters, like if greater than X, then good, gave some decent results for honey predictions. So after we've gone through and we've looked at all the data, and we've gone through all this analysis and selected the weather and selected the satellites and everything else as well, and cleaned it all up and made this big database. That's the code. It's not very much. So basically, you've got inbuilt regression, machine learning regression libraries in Python or in scikit-learn. And so basically, you go through and you start here and you split your data into a testing phase and a training and testing set. You go through and you fit the training set, and then you test that on the test set, and then you got a model. So in terms of the actual amount of work done, the amount of work doing your data preparation is exponentially more than the actual modeling itself. It's ridiculous how much time you spend just getting your data looking nice and pretty. And then you obviously play around the parameters and test different things, but it really comes down to garbage in, garbage out. Get your data set done well at the start, and from that you'll get a good result. So this is some of the approach you can use. So random forest is basically kind of like a if-then. So this is if transpiration in January is above or below 9.8, then go this way or this way. And then if the solar radiation is above this, go this, and it trees its way down. Obviously, one tree is not very reliable, so the random forest actually produces a whole what's called a forest of trees, and then uses that to make the best outcome based on an analysis of more than one tree. Gradient boosting looks at the effects of variables at different times, rather than sort of having a straight linear relationship. You can see that there's non-linear points here, which are very important. So this is the average temperature from November to February, and you can see once you get below 27 degrees, you get a stepwise increase in honey production, pretty much. So this is a really useful one in terms of where you have non-linear relationships, which is pretty common in agricultural work. So this is an example of gross primary productivity, which is a measure of solar exposure and everything else as well over a year. In this case, and you can see there's again a stepwise change rate here. So this process is done for all the variables, and then you can start looking at which ones have the greatest impact or dependence on the outcome, and you can start scaling them down. So this is the average error for the honey weight, so plus minus 10 kilos per hive if you use all 200 variables. And you can actually go down to 4 or 5 variables and still get a pretty similar result, which obviously if you're looking to roll this out to industry and have a similar automated process, having a low number of variables that gives you the similar accuracy is a pretty handy result for ease of implementation. So in terms of the research, we developed the model and we did a test on the 2020 season on a few different sites. And so what we did was we started doing a prediction from the start of November, and then every month we did a new prediction as we got more the next month of weather and solar that are online. And you can see you've got 2 sites that were the actual harvest per hive was pretty similar, and the Chittering one north of Perth was pretty low. You can see that the Harvey one was a bit low, then was pretty close at the end. The Byford one came in a lot higher, and interestingly, Byford is on this particular site is on the edge of the scarp, and we know there's a strong temperature rainfall gradient at this place. So we suspect that the issues with this one, with the error, was due to the location and the inability of the data sets to pick up those strong gradients in your rainfall and temperature. And then Chittering from the start it knew it was going to be a poor year up from the start. So this was a test case, so great. We've got a working prototype. This is a model with a geospatial portal with industry now. And so with this portal, beekeepers can log in. They can see just their own sites, and it's got a prediction of the honey harvest, again graded from red through to yellow to green. You've got your last week of temperature and rainfall, and then the monthly values, temperature, rainfall for the last few months. So you can get a feel of different sites, what's going on, and then the actual honey prediction through there. And so the process we went through season just gone was we issued the first prediction to beekeepers at the start of October, and every month we updated the model and gave them new information, and it had notes around the climate projections for the next 3 months as well. And so we thought, okay, it was a cool November last year, good harvest, but it didn't feel quite right. While cool November was unequivocally a result in a good harvest in the models previously and all the simulations, it wasn't looking how I thought it should look by the end of November. Because by November, you should start seeing little buds forming, an actual physical response from the October period. And what happened was this. So this graph on the left, the blue line is the average solar exposure. So I measured the actual energy in joules from the sun per square meter. This is the average over the last couple of decades for the Southwest. And this is what happened in October last year. We had slightly above average October in terms of it was a bit warmer and drier than usual. And November was actually pretty cold and wet. we know from the physiology of the trees and obviously simulations as well that that period is crucial for the bud initiation phase. And you look at, there's a number of our native bees actually, they have an annual breeding cycle and actually nest underground most of the year. They pop out in December for a few weeks and have at it, and then go lay eggs, nest again. And through the Southwest, almost none of them even emerges here. It actually elects to have a 2-year hibernation cycle rather than 1 year based on the spring data. And on the right here, you've got, this is the sort of the soil exposure difference over that period from 2020 and then all the previous data points. And so you can see that we're working well outside of where the model data was. So if you look at this across the state, this is a map of the locations we had data for. This is what you normally get. So you can normally get a, in a good year, you get, or average year, you get a increase in your soil exposure across the months. And then this is what happened last year. And so basically the cues for bud initiation in red gum and a lot of species just did not happen at all. Preliminary indications are that there was a cutoff point at which the trees did flower. And so we know there was some honey harvested for some of these locations here and here in some areas. Beekeepers are just getting to their quiet period now. So I'm hoping to meet up with some more of the commercial guys and have interviews with them to actually collect the data on which sites were formed. But an exceptionally unseasonal year for the first year of trying to roll out industry, which is very unfortunate. So we had, based on October, November predictions, we were saying, oh, it's going to be a bumper crop. When we sent it out, I sent out with caveat saying, model says this, but we haven't had this kind of year before. So this is the prediction versus the long-term averages. So it was looking like, like being a bumper crop. In reality, most sites didn't even flower. So most trees actually completely missed the cue to form buds and even start the process. So we're lucky we got about 10 kilos per hive of one of our sites. I know if your commercial guys got 20 or 30 kilos of hives, they're sort of sitting around here. But certainly a very different results to what, and this comes down to looking at, modeling process and making sure you know where your limits are, where your data is. And if anything is outside of what you've modeled, be very, very aware of that. So in terms of, the bigger picture, for ASDAF and satellite data and machine learning everything as well, not trying to do. So obviously the research is very good, but if you can give a result to industry that's useful, that's even better. Be aware of input limitations in terms of how you collect your data, how the data lines up with your models and everything as well. The amount of data available is ridiculous. The amount of different sources and products you can get these days is absolutely crazy. So you need to make sure you know what you want and do your lit review and make sure you know which are likely to give you best results in the first place. Otherwise, you're going to wind up with a massive input data set with a lot of not useful data. As a part of that, you need to make sure you put your effort into that data prep. That's really what it comes down to. I'm lucky in the bee industry and that I'm beekeeping myself, and I work a lot with commercial guys for the research, and so they've got decades and decades of handwritten notes around what seasons are good, what seasons are bad, everything as well. So there's a lot of wealth of data there as well. And the idea of having both a domain expert and a data science expert is a really good partnership to have. So you can have someone that can do all the coding and numbers, but someone actually say, well, this makes sense, this doesn't make sense, or I remember back in 1969 when this happened with this one tree somewhere, and that might be some useful data for you as well. So really, if you want to get an industry result, that partnership is really important. Any questions?
I don't know whether I should just speak from the board.
I can hear you.
Excellent. Well, thank you so much for that, Tristan. I'm Asha Stabak, the Business Development Manager for the Space Data Analysis Facility. So thank you on behalf of everyone for today. I don't know whether you just want to come over to the screen and let's say a hi to, we can only see a very small part of your face standing off to the side. So We have about 17 people joining us online. And I've got a question from Ross, who said, excellent work in predicting future honey harvests using remote sensing and weather data in the machine learning models. Are you able to use this process to also predict probability of colony failure based on various stress factors?
In terms of, I'd say qualified yes for WA. If you know you got a bad harvest coming up, then your winter resilience will be a lot lower. Colony collapse is more of an issue in terms of bee health, and so that's more looking at the actual the queen's age, the queen health, exposure to pesticides. In terms of using this model to make that prediction elsewhere, I'd say no. That's more around actually monitoring the internal function of the beehive, and of course you can feed your bees supplementary feeds or artificial pollen if your stores are low. So certainly overall health for WA, yes, but in terms of taking it elsewhere in the world, that's more of a region-specific hive management system. But certainly in terms of machine learning and the approaches, there's a lot of work being done actually having instrument beehives where you have internal sensors to look at your humidity, your density, your queen activity, your food weight, and they're working on ways to use those to predict colony health based on combination of the environment and the internal hive measures as well.
Excellent, thank you so much. And a question for me, I think you raised particularly at the end around having a cool November and I guess that impact in terms of the data and having those domain experts. Have you actually been able to draw on, like, have they got data, or is it a lot of it almost like a bit of a gut instinct from some of those people that have been out in the fields and things like that?
It varies a lot. So when you're working with commercial beekeepers, a lot of them do have ISO quality assured systems in place, and so that means they actually have 5, 10 plus years of audited records in place, which is invaluable. Going back longer than that into so the 90s and 80s and 60s, there's a lot of really good stories. But again, like the confirmation bias on those is difficult. So we can look at individual data points. It's hard to use that for a industry-wide perspective.
Excellent, thank you. There haven't been any other questions coming through on the chat line here, but I'll pass it over to those that are in the audience in case they've got some questions as well. Thank you.
Yes.
Yeah, so at the beginning, you mentioned that these hives have moved.
Yes.
So how many kilometers will a particular hive cover in a 12-month period, like just to get it to the right place?
Up to a couple of thousand. So typically, commercial beekeepers will move their hives every 4 to 8 weeks, depending on the flow. And from Kalbarri to Bridgetown over the year isn't unusual. Every couple of years, there's a really good honey flow in the goldfields, and so you actually go out as far as Kalgoorlie. And while it's a long way to go, when the mallee trees there flower well, one of my friends, he was producing as much as 20 kilos of honey per hive every 5 days. It's just ridiculous. So basically, he would drive out there, he'd prep the hives for harvest, harvest the hives, drive back, extract the honey, and drive out again the next day. He was doing that for about 6 weeks. So an average beekeeper, in terms of they will drive 100,000 k's easily just with their truck, let alone with their ute doing scouting trips as well. So it's a lot. But that's less than what happens in the US. In the US, you have most of the commercial beekeepers focus on pollination contracts, a number of their hives from Florida to New York State to California every year. And they'll literally go almost across the entire continent every year. So we don't go that far in WA. Yeah, it's pretty big undertaking. Yes.
Due to the dramatic effect of smoke on bees, are the authorities duly bound to advising the industry when they carry out controlled burns or in areas? Or
yes, so not necessarily the smoke, but actually, obviously, if they burn through an area and you've got beehives there, the beehives will be gone. So when you do have your bees on Crown land, you do get a notification 6 months out from a planned burn area, and you have to, and you can't use that site for that season pretty much.
We have another question from online. So thanks, Tristan. Are you able to control for the amount of honey consumed by the colony that occurs between flowering and the harvest?
During a honey flow, that's not an issue in terms of the red gum. So if the red gum flowers for that sort of 6 to 8 week period, and basically as soon as the weight of the hives stops increasing as fast, so not say it goes backwards, but they start slowing down their production. Generally, that means it's time to move into your winter phase, and so you'll actually shrink the hives down and move them up north. So in terms of the prediction, it's not relevant to this particular harvest. It's more around the hive management and the hive health of the stores.
Thank you. I don't think there's any other questions from the online audience.
Okay. Well, thank you so much, Tristan, for this talk. I think that's it for today. Thank you for joining us. And for future events, just keep an eye out on our website. So thanks again, everyone.